Good morning, bonjour. Thanks to everyone for those who rose early. I want to, of course, add my voice of thank you to the organizers for giving me the opportunity to speak here at Praxis. This is kind of a homecoming for me. I was a postdoc here in Paris, not just down the street. I lived on la Rue Mouffetard. It was incredible. It was my best experience of my life. So I'm really happy to be back here. Very good. So what I'm going to be talking about today is the idea or the question of how one achieves in a quantum device something that we think cannot be accomplished with a classical computer. And that has been, that term has been given the term quantum supremacy. I know that's a loaded term. I'm going to call it QCS, quantum computational supremacy. And I think this is an important concept, so let's just try to frame what we're talking about here. So, you know, the foundations of computational theory tell us that, or at least conjecture that, there are certain hierarchies of classes of problems in terms of how hard they are to solve. And Church and Turing set down the idea that basically all things that computed efficiently were in the same class, and they would all be able to be computed on a Turing machine. So any easy calculation, one that, from a computer science point of view, we say scales polynomial with the size of the problem, is one that could be solved on a Turing machine. Now, as a physicist, I think we're proud to say that we have some impact on this question that seems to be a purely mathematical question. It says that these questions about what is computable is actually tied to the physics of the device, and not all physically reasonable devices are equivalent. If the device is governed by the laws of quantum mechanics, then perhaps, we hope, we think this extended Church-Turing thesis is violated. And so it's one of the challenges of our time right now to see if that's true, to see if we can demonstrate something, anything that violates that. And that's what this business about QCS is about. It's about somehow demonstrating a computation that we believe cannot be done efficiently with the best classical supercomputers today. Okay? Now, I would say I'm not a I'm a real novice, I would say, in the foundations of computer science. But from my understanding of it, of course, it's a bit of a slippery business because nothing is really proven in the classical regime either, where the separation with this belief of a hierarchy of complexity is a strong belief, but it's not one that is proven. It's all conjectures in the end anyway. However, we take as given that there is this hierarchy, and then we just say, okay, given the best we know, what's the best we can do? Let's try to construct some task that we're going to try to do on our quantum device and see, with the best supercomputers we got around, whether we can beat it. All right, now more jargon. These days, one of the hot topics is what's called NISQ technology. And John Freskel, you know, he coined the term quantum supremacy. He coined the term NISQ. He's kind of the trendsetter in this business. And the question now, you know, given the technologies we have at the moment, we may not have the universal fault-tolerant quantum computer. If we did, we'd try to solve Schur's algorithm, even there, we don't really know where Schwar's algorithm sits. Maybe there is a classically efficient algorithm for factoring, but we feel reasonably confident. We don't have one. So, but that would certainly be a demonstration of QCS. But we don't have one of those right now. So what might else we try? Well, one of the directions, of course, that's incredibly interesting that many of us are pursuing is a kind of special purpose quantum computer, what we might call a quantum simulator. A quantum simulator is typically thought to be, what I mean by this is an analog machine, and that might be a quantum annealer in the spirit of the D-wave computer, or it might be what we heard, the beautiful talks we've heard at this meeting, for example, from Jean-Michel Raymond about quantum simulation with Rydberg atoms, or from Sylvain Schwarz as well. So this is one path to thinking about achieving this QCS. Another path that is being explored, particularly at Google, is this idea of what's called sampling, using sampling of complex probability distributions to try to demonstrate this QCS. These problems are not unrelated. I'll come back to that in a moment. And to do that, I just want to talk a little bit about the business about analog quantum simulation. I mean, there are beautiful experiments. I'm an AMO physicist, so I am particularly taken by the experiments in cold atoms, be they charged or neutrals, and one can manipulate these many body systems. We heard an example from Sylvain at the beginning of this meeting. And when one does an experiment on such a device, there are sort of different aspects of it. One aspect of it is what I would say is examining the microstate of the system. What I mean by that is, for example, here's an example that I had taken at the time. This is from Marcus Grinder's group of work done back in 2011, where they were looking at a Bose-Hubbard model to simulate antiferromagnetic to paramagnetic order. And this is their, sort of fresh off the presses quantum gas microscope, where they can look at individual atoms and see whether there was an atom in the trap or not, and read that out. And there's a certain configuration of zeros and ones, atom, no atom. And that configuration is, of course, what is a microstate of the many-body system. And that microstate happens with some probability. That probability I've written in a very formal way in terms of the projections onto up or down in terms of the Pauli operators. And what you see, of course, is that this probability distribution depends on all moments of the distribution, right? It's a very, 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 very high order correlation function, this microstate. On the other hand, when we're doing a quantum simulation, we're typically not interested in this. What we're interested in is some phase transition, right? That phase transition is characterized by some order parameter, which is some low order correlation in the system. And so what one does is one takes those microstates, takes ensemble averages, and from that tries to observe some change in the order and to simulate a phase transition. Okay? So now I want to think about bringing these ideas together. So we talked about the different ways in which we might try to achieve QCS. Sampling complexity is one of them. So let me just remind you what we're talking about when we're talking about sampling complexity. When we're talking about sampling complexity, well, we're asking the following question. What is the complexity of an algorithm that would spit out random numbers according to a certain probability distribution. So I have some probability distribution, and I have some device, I push some buttons, and it spits out this, right? Or then I push the button again, and it spits out this. And then I push the button again, and it spits out this. So I'm spitting out random numbers, but those random numbers are hopefully not just uniform over the distribution, but they're weighted appropriately according to this probability distribution. And we want that probability distribution to be really, 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 really hard to calculate. So we really would be very hard for us in a classical computer to know which are very highly probable outputs and which are the outputs that are going to happen with very low probability. An analogy that I've heard that I think is a good one is we should think about this as a kind of speckle pattern in exponential Hilbert space, right? I mean, this speckle pattern is coming from the interference of many paths, in this case in two-dimensional space. And there are many, many, many rays that can go that interfere, that either constructively or destructively interfere. What we want in our quantum device is to create some kind of speckle pattern in exponentially large Hilbert space and then sample from that. And the idea is that that would be, if we can do that, and we'll come to explain why, that would be a demonstration of QCS. All right. Now, I just want to make the connection to analog quantum simulation, or for that matter, any quantum computation. Any quantum computation, I would argue, is a sampling experiment, right? I mean, we create a quantum state, and we measure it, and we get some output with a certain probability. I mean, Schwarz algorithm was so clever because it was designed to make the right answers constructively interfere and the wrong answers destructively interfere, so that the right answers were concentrated, and you didn't have to sample that distribution many times to get the right answer. In a quantum simulation, again, as we said, we sample, we had those microstates, we get a particular string of zeros and ones, but then at the end of the day, we might get an order parameter. We use the samples. We're not just interested in whether we get samples or not. We're solving what we might say is a decision problem. We're solving for this. And I think it's an important question. I just put this out here. How much complexity do we need in any probability distribution to demonstrate QCS? I mean, just because we measure an order parameter doesn't mean it was hard to calculate that order parameter, even though it might live in an exponentially large Hilbert space. Moreover, I think there is a very strong connection between how hard it is to generate the complexity that's necessary in a probability distribution to get QCS and the sensitivity or robustness. What I would conjecture is that the problems that are easy to solve are robust. The problems that are hard to solve are most likely very sensitive to imperfections. So that really does, I think, raise some questions of whether an analog quantum simulation is going to allow us to access QCS. Just because we've done a quantum simulation doesn't mean that we've done something that we couldn't do efficiently on a classical computer, because for God's sakes, we're physicists. We see an experiment. Our goal is to explain the data. We don't have to use matrix product states to necessarily explain a mean field phenomenon, right? We don't need the big Hilbert space, so we should be careful in this context. All right, with all of that said, what I'm really now interested in is the question, what would it take, can we see this complexity? And I'm going to look at sampling as the role. Now, sampling complexity was first brought to the fore in one of the most unlikely places from a quantum optician's point of view, linear optics. I mean, linear optics is as classical as it gets, but at least maybe I'm not as sophisticated as other quantum opticians, but from my point of view, for God's sakes, you know, that seemed to be the last place on Earth I would imagine to see something that would demonstrate some kind of QCS. And this was first discussed by Scott Aaronson and the student Arkhipov, and I'll just quickly explain it if you haven't seen it in the past. So a linear optical device is one, of course, that just is linear. The input-output relation of the creation annihilation operators is linear, some linear combination here. And we have this linear optical network here that is characterized by this transition matrix lambda. Okay? And the idea, of course, we have to send in non-classical light if we're going to do anything non-classical. They considered single photon states. And we want to then look at the output state, which is the scattering operator, the S matrix operating on the quantum state. All right? Now, this is a particular history, right? This input photon goes to that device. These colors are just here to guide the eye. They're all identical photons, all at the same color. I'm just drawing these. I don't know if the colors show up good enough. You can see the difference. These are some of my favorite colors. So here's just two different paths. In this first path, I just exchanged now photon 2 goes to output 1, and photon 1 goes to output 2. And you see all I did was exchange those transition amplitudes. And so well, of course, in quantum mechanics, all the possible histories of the ways those photons can go to the director, I have to add the amplitudes for them to happen. And there are factorial number of those, or exponential number of those. And so the final probability, for example, as one example, to see a particular configuration with one photon at each output port would be given by the square of the sum of all of these permutations, okay, for all of these that end in a particular way. And that sum of permutations is what's known as the permanent, right? It's like the determinant of the matrix, but without the minus signs. And it's the permanent because these are bosons. If they were fermions, then I would have the minus signs upon exchange, and then that would give me the determinant of this matrix. All right? And if I have some other configuration with not just one photon at a given site, but some number at a given, then it's the permanent of some other matrix where I've repeated columns or rows of this matrix the number of times that I see a particular photon at that output. All right, here we go then. So why is this interesting from the point of view of QCS? Well, firstly, it turns out that calculating the permanent is really, really hard, unlike the determinant. You know, yes?
Isn't it because we haven't found a good method? Is it really known that it's hard? It's just that there might not be a...
So, okay. So I would say a few things. One is that we know that a generic matrix with both positive and negative entries, that even approximating the permanent of that matrix to within what's called multiplicative approximation. That is to say, if the permanent is really tiny, we need to approximate it even better so that our epsilon is proportional to the size of the permanent. That even doing that is in a particular computational class, which is called sharp P, or number P. That class is the a particular computational class which counts. It's not as just solving the traveling salesman problem. It's counting the number of positive solutions to the traveling salesman problem. And in the theory of computational hierarchy, that's outside the whole polynomial hierarchy. So if what you say is true, then the whole polynomial hierarchy would collapse. And all of, so we don't know. We absolutely don't know. But it's like, it's the whole, you know, maybe house of cards upon which computational complexity lies. So this whole business, I mean, we don't know that factoring is not easy either. So I would say it's about what we take as a given. If we believe there is a hierarchy of hard problems, this problem sits way the heck out there. It's above the whole polynomial hierarchy. Okay, so I can't even approximate this problem easily. And it's a known result from computer science that if I could sample from this distribution that is a function of the permanent, if there was this magic box that I could push buttons on and would spit out random numbers on the speckle pattern according to this interference of the exponential paths, then there exists a way of approximating the permanent well a little bit above, somewhere up in the polynomial hierarchy, like 2 steps up, okay? It's not efficient, but not as hard as sharp P. And so the polynomial hierarchy would collapse to the 3rd level, we say, okay? So this is the argument for those of you who are interested in why we say this is hard. It's about this hierarchy of complexities, okay? All right, so what I'm here, I guess I've used a lot of time in my introduction, but what the heck? What I'm really here to tell you about today is thinking about, instead of linear optical networks, thinking about atoms and optical lattices as another platform for exploring this sampling complexity of identical bosons, non-interacting identical bosons. My interest in this is twofold, maybe 3. This problem was surprisingly exhibited QCS. That was a surprise. Can I make the problem even simpler and still see QCS? I mean, here every mode talks to every other mode through some beam splitter. If I only have nearest neighbor hopping, and if that hopping is, for example, uniform, is that enough to generate QCS? The other reason I'm interested in, and perhaps I'm more interested for that reason, is that I think potentially this is if we really wanted to do this with something like 50 or 100 bosons, doing them with atoms is probably better. It's probably easier to trap and detect and cool 100 atoms well than it is to make 50 identical photons and detect them with perfect quantum efficient and not lose them. So that's another. And I also, this allows me to explore the relationship to quantum simulation. We could start putting interactions between these bosons. And that connects us to the whole Bose-Hubbard or Fermi-Hubbard or other examples, and see this relationship between the complexity of a microstate and the complexity of an order parameter and its relationship to QCS. So that's the broader program that I'm interested in pursuing. Okay, we call this a quantum random walker. It's a kind of misnomer. I mean, nothing's random about it. This is just deterministic Schrodinger evolution, but it's sometimes called a quantum random walk because we think about if an atom can tunnel to the left or tunnel to the right, it does so randomly. And If it was a classical random walker, it would be diffusive Gaussian distribution. And if it's quantum, we get interference between all those random walks, and an individual atom would have a wave function that has this shape. Okay? This is a single atom wave function, not the many atom wave function. I mean, I want to maybe just back up and emphasize one of the things I think is important about this problem is that at the end of the day, the non-classicality here is coming in the many body physics in a strange way. It's coming from the fact that these are identical particles. You could think about it as mode entanglement from a wave perspective, but there's no particle-particle entanglement. These are non-interacting atoms under assumption or photons. Okay, so let's just start with the simplest example. Let's just think about nearest neighbor hopping with some hopping amplitude j. I've written the Hamiltonian in second quantized form. This is, it's the one body Hamiltonian here. And of course, that's a trivial problem. I mean, that's the tight binding approximation. That's band structure. For God's sakes, I mean, we can diagonalize that instantly by just writing it in terms of the block states. And we have the band structure. In this case, the tight binding band structure is just the cosine of the quasi-momentum. So is that hard? Well, we can't really answer it. One of the things that's important is that if we want to, what we want to ask the question is, what is the probability of finding, I have n atoms, they're all initialized in these lattice sites, I let them tunnel ballistically, and now I want to count the number of atoms in a given lattice site. What's the probability of that happening? Well, I have to change to the Wannier basis, the lattice site basis. All right, that's easy enough to do. Just take the Fourier transform. I got some Bessel functions if I like. And I have the same problem that I had for the linear optical network, but now instead of my scattering matrix, I have the time evolution operator. And at some time, I just stop and I ask this probability is the permanent of this matrix, lambda. So now the question is calculating the permanent of that matrix hard or not? That's not the whole story, but that's at least one part of the story. This matrix is not a speckle pattern kind of matrix. It's a very structured matrix. It's a matrix that has what's called the Toklas form, where everything on with the matrix elements only depend on the difference in the indices here. And that's because because this is a translationally invariant system, it only depends on the distance that L goes to L prime, okay? So the matrix elements in the Wannier basis look like that wave function for a single atom, okay? And it's a band, if we don't let the atoms tunnel very far, then it's what we would call a banded Toklas matrix, because these would be zero or very close to zero outside the time it takes for the atoms to ballistically tunnel. And if I put on periodic boundary conditions, that's what we're seeing over here, but the boundary conditions aren't really important. We can fix that in the end. Okay. So this is a banded Toklas matrix. So the question is, so then we went into the literature and say, well, is calculating the permanent of that hard or easy? Well, it depends. For a generic matrix, the best known algorithms for calculating an arbitrary permanent scale exponentially with the size of the matrix, n. But if I have a banded Toklas matrix, we have this kind of scaling. This is at least the best known algorithm, okay, that we could find. It was not so long ago written down. And this matrix scales essentially exponentially with the size of that band and logarithmically with the size of the matrix. If we wanted to include the boundary conditions on that, then we can make that a more generic matrix which scales exponentially with the tree width. There's this is a combinatoric problem, and there's a relationship between calculating the permanent and the perfect covering of certain graphs. Okay, and the tree width is another way of expressing that. So, what we see for this problem is two cases. One, if we don't allow the atoms to tunnel very far, if we keep the time constant or not going more than polylogarithmically with the size of the matrix, well then the band doesn't grow with n, and then we can calculate the permanent in a time that's logarithmic we can calculate the permanent in a time that's polynomial in the size of the matrix. So that would be an easy case. There's certainly no QCS in that case, and that's obvious. On the other hand, if we let the atoms tunnel for a long time, for a time that grows proportional to the size of the system, well then, at least these, the Schwarz algorithm grows exponentially. The size, the long time it takes for it to calculate the permanent grows exponentially. So in that case, even the most trivial case seems hard. Now, again, let me just sketch this out. We're conjecturing that this is hard. We haven't really proven it. It's hard to prove anything in this case, because what we really need to prove is that there is no algorithm that can approximate the permanent efficiently given some noise in the system. We haven't done that. We just think it's a curiosity to start that even a 1D problem with nearest neighbor hopping, there's no obvious way that we can find. And I find that to be a curious fact. Even the most trivial problem of tight binding band structure has surprising complexity in the microstate, it seems. And it's just because there is an interference between an exponential number of paths which lead the atom to a particular lattice site. All right, so now we really want to go beyond this Toplas structure and ask the following question. Can we, with our atom lattice system, 1D atom lattice systems, can we do the same thing that's being done with linear optics? Okay? And in order to do that, what we need is those matrices, those transition matrices, to be speckle patterns. We need them to be Haar-random matrices, okay? And in the case of linear optics, we could do that because we could put just random beam splitters and phase shifters, and that would generate a Haar-random matrix. But when we only have nearest neighbor hopping, that's not so easy. So let me just say a few words just to remind you about Haar-randomness. What we mean by Haar-randomness is a random unitary that is randomly picked according to a measure that respects the group structure, in this case of the unitary group UD. Oops. And it's easy to generate such random matrices. You just take Gaussian random complex number, and then you orthonormalize the columns. That's a Haar-random matrix. The columns of those matrices are what we would call random states in Hilbert space. And they have certain statistics. If we were to ask what's the probability of seeing a certain square amplitude, let's say probability to find an atom at a given lattice site, we could just marginalize that. That's what's known as the Porter-Thomas distribution. It's far, even though it's random in Hilbert space, it's not the uniform distribution in terms of the computational basis. That's very important. It's got those speckles in it, all right? And the entropy of those entries for a random state, on average, averaged over the Porter-Thomas distribution, is not log D, but it's got this extra amount. That's the sort of extra information we have per state. Okay, that was looked at some time ago now by Bill Wooters. All right, so how are we going to try to do that? If we had arbitrary hopping between different lattice sites, well then that's trivial. We just can map it onto beam splitters and phase shifters in the same way. But we don't have that. But what we do have is the ability to do optimal control. We have the ability for time dependence in the problem. So the question we can ask ourselves is, can we, by modulating our atom lattice in some way, generate a target Haar-random unitary? The answer is yes. I wouldn't be telling you otherwise, just like Howard said. So our system, we're going to generalize our atom lattice a little bit now, just because this is a system I know and love for a long time, to think about a Spinor lattice. So we have a lattice of two kinds of atoms in two different internal levels, one we call spin up, one we call spin down. We can trap the spin up atoms relative to the spin down atoms in two standing waves, one's right and one left hand circularly polarized, and we can shift those two standing waves relative to one another. And in doing so, we can affect the tunneling matrix element going to the left versus going to the right by this parameter theta. And we can also drive hopping. In this case, we're going to assume a very deep lattice, neglect any tunneling within a given spin, and the tunneling is spin-induced hopping, say, by a microwave. This might be a hyperfine splitting of 10 gigahertz, and we have microwaves that flip spins up to spin down, and accompanying that, the atom hops, either to the left or to the right. Okay? So, in this community, I don't need to tell you about the whole business about controllability. We need to ask ourselves whether we can generate the Lie algebra, in this case, SUD for D lattice or D-dimensional system. Okay, this is our Hamiltonian. I failed to mention that in addition to the hopping up to the right, we also included a quadratic potential that breaks the translational symmetry. We needed to do that to make the system controllable. Otherwise, well, it wouldn't be. All right, so this is our Hamiltonian with hopping to the left and the right and a quadratic potential over here. And the system's controllable. You know, we did it. We checked the Lie algebra, it's controllable. Voila. And the control parameters in this case are the anchor parameters theta, which tell us the overlap going to the left and going to the right, and phi, the phase of the microwave. Okay? So, with that, we can control waveforms, for example, to take an atom localized in any site and transform it through the controls to a desired random state on the lattice. And what we need to be able to do is to do that simultaneously for atoms localized at every lattice site. So an atom localized at every lattice site must, at the same time, with the same global control, go to an orthogonal random state. Okay? But I emphasize this is single atom control. We're not controlling the many-body system. We're just controlling the state of one atom. And depending on where it started, it goes to some random state. Okay? That's the beauty. We don't have to generate the 2 to the n dimensional unitary matrix on n qubits. We just have to generate the n-dimensional matrix n by n, where n is the number of lattice sites on the system. All right. So we do that with grape. Grape is great. It works. We love it. And we did our numerical simulation this is what a waveform looks like. Doesn't really mean anything, but we can get, high fidelity, infidelities, as many nines as we want. Those of you who have played around with wave know how well it works. All right. Now, how much time do I have left, sir? Okay, oh, good. I've rushed, so I can slow down a little bit. What I just described to you was the optimal control problem, which said, I want to design the angles and phases to generate a particular target Haar-random unitary, okay? And it's well studied in the quantum control community that typically, or not typically, generally, there is a quantum speed limit. There's given a certain amount of energy and bandwidth in the system, there's only so fast you can do that, you can get to that, okay? So there's a kind of, if I thought about this as a bunch of piecewise constant values of my thetas and phis, there's a kind of minimal number of these little pulses I need to get to an arbitrary target in the system. That's what's known as the quantum speed limit. However, for the problem at hand, it's not that important that, we're not solving a decision problem, right? In a decision problem like Schwarz algorithm, I got to make that unitary matrix because that's the one that does the quantum Fourier transform that lets me factor numbers. That's not what we're doing here. We just want to make sure that it's a speckle pattern in the class of all speckle patterns, okay? And for that, we might say, I don't need no stinking optimal control. All I need is to randomize my controls and just randomly pick thetas and phis. What is the overall map that we get in that circumstance? So we did just a quick little test on that in the following way. What I'm showing you is two different graphs on top of one another. The orange curve is our optimal control algorithm. So what we do is we say, here's a target unitary sampled from the Haar measure, optimal control. Make that target unitary. And we do that allowing a certain number of these pulses, piecewise constant versions of our controls. And as we add more and more, we ask the computer, what's the best fidelity you can get? This is a way of numerically extracting the quantum speed limit. And what you see is it takes, about, d squared on the order of d squared steps to get there. That's expected because, well, we have d squared parameters in our d by d unitary, okay? On the other hand, I can ask myself, okay, now instead of doing optimal control, I'm just going to do random pulses and concatenate them. And then ask for the total matrix I get after I've concatenated a series of these pulses, what is the entropy of the columns of those matrices? And what we see is the entropy very quickly and much more rapidly asymptotes to the value that's expected from Wooter's formula. So what that's saying is that the system is mixing, randomizing, blending into a Haar-random unitary much more rapidly. The speed limit for achieving Haar-randomness is faster than the speed to reach a particular target. That's an intuitive concept, I think. And we further checked other tests for that. We looked at the Porter-Thomas distribution, and we see indeed that does fit quite well. Now, one of the questions we're interested in, and this is a sort of still work in progress, is the question of how random is random? In general, these matrices, these transition elements, or you might call, are pseudo-random. And one way of quantifying pseudo-randomness is through this concept of what's known as a T-design, a unitary T-design. A T-design is not an ensemble that is picked according to the desired measure, but it's an ensemble that captures certain moments of the distribution, only up to order T. So it doesn't necessarily capture all the complexity, all the high order correlations, but just up to order T. That's what's known as a T-design. So a question of interest is what level of pseudo-randomness is necessary for QCS? Do we need full Haar randomness? That seems to be a high bar. At what point, what level of correlations are necessary in order to achieve? And this is some work that is very closely related to the work of Daniel Wugarth, who's here in the audience. We discovered this paper after we played around with this, and we're learning a lot from this and trying to make these connections as well. All right, one last point. Verification. So, all right, let's say we made this Haar random unitary, or we made the pseudo Haar random unitary, and we're taking these samples. We're just taking them. How the heck do we know that we've done anything? Well, it's a hard problem. I mean, unlike factoring, there's no way, it's not a NP hard problem. It's not an NP problem where you plug it back in, there's a polynomial algorithm that tells you whether that was the right answer or not. Well, one way to look at this is to say, well, maybe we could just trust physics. That is to say, we know that the atoms are obeying the Schrodinger equation, and we test all the components in it. We check that we prepare atoms with a certain fidelity. We do the best randomized benchmarking and other verifications that we've made the right single atom unitary map. We check that we are detecting these atoms with high efficiency. Maybe that is enough. Not clear. But a question that if we want to go this route, we have to ask our question for our friends in the laboratory. What is the actual threshold? How well do I have to do? What is the, I'm not going to do it perfectly. So what is the threshold for being close enough to the right distribution? I think that's an important point, important question that I don't know the answer to, and I don't think anyone else does either. Finally, we might just say, well, maybe we don't care about QCS. We just want to demonstrate that we're doing something that is hard. And this is the way that Google is going. And what they're saying is, OK, we're going to check our answer according to a classical computer. The classical computer can tell us, if we run it long enough, what the ideal probability distribution is. It'd be very hard to do it, but they got a lot of computing power to do it, so they do it, and then they compare that to what they measure experimentally, and thereby see that they are creating pretty highly correlated, pretty highly entangled systems. I think this is, in my view, interesting in its own right, even if we can't say that we've collapsed the polynomial hierarchy. I think it's still a very interesting question to push the frontier to see how much correlations we can generate in a system. And I hope these atom lattice problems are a way to get there. So I'll stop there.